Dear students, in today's lecture we will study about three sections of chapter 4. In these three sections, first section deals with the internal generated voltage of a synchronous generator, and the second section is dealing with uh, the equivalent circuit of a synchronous generator. At the end of the lecture we will discuss the phasor diagram of a synchronous generator. So first of all, the internal generated voltage. So this is the equation, which is basically uh, an equation for the internal voltage, which was already derived in previous chapter. We derived this. So this is the equation usually used to find the internal voltage. So internal RMS voltage can be obtained by this green formula. The expression can be modified in terms of machine design constant and the parameters that are variable during machine operation. The flux and the angular speed of the rotor or electrical frequency in radian per seconds. Now you can see that this is the section which deals with the electrical frequency. On the right side we express the equation in terms of mechanical frequency. If we come on the left side, we can see that the same equation can be written in this form if we multiply and divide by 2, by constant 2, or we can write 2 pi f is equal to omega, as we have studied in previous classes, that 2 pi f is omega. So we will put, this is omega E. E stands for electrical. So this is a basic equation for RMS voltage, and then we write this NC over under root 2. We equate this equal to a constant K. But we studied that the relationship between electrical frequency and mechanical frequency is somehow like P by 2 over into omega m. So omega E is equal to P by 2 of omega m, which means if number of poles are P, let's suppose 2 poles, then 2 over 2 would be 1, so omega E would be equal to omega m. If there are 4 poles, then it would be 4 by 2, 2, so it would be omega E is equal to 2 omega m. So this is the main theme. So the small p is the number of poles, while this capital P can also be written if we are considering pole pairs of the machine. So this is a summary for 2 poles, in which this is the formula for dealing with mechanical frequency, and this is the formula dealing with electrical frequency. So this is the same RMS voltage formula which we have just studied. In this formula we can see that E of A is proportional to the flux and the rotor speed. This is the mechanical speed of the rotor, and this is flux. So E of A is directly proportional to flux and omega m. But we know that flux depends upon the I of F. Flux depends on the current, and so if we apply the transitive property, we can say E of A is directly proportional to the flux and flux is directly proportional to the I of F. It means E of A is directly proportional to I of F. Over here in figure A, the relationship between phi with I of F is given. In figure B, the relationship between E of A against I of F is given. In both the cases, the first, the current, the flux increases with the increase in the current, and it becomes constant in both the cases when the saturation occurs. Now we come to the section which deals with the equivalent circuit of synchronous generators. In this diagram, it has been shown that this is basically the equivalent circuit of a synchronous generator which has three phase voltages. So we will study this in detail, and at the end we will be able to derive this equivalent circuit. So let's start. E of A is the internal generated voltage. So the same voltage appears at the terminals of the machine only and only if there is no current in the stator winding, and there will not be any current in the winding only if there is no load connected to the generator. If there is no load connected to the generator, there would not be any current passing through the stator winding, and if there would not be any current passing through the stator winding, then the EA would be equal to E flux. E flux is basically the output voltage. But if some load is connected, then EA would not be equal to output voltage or terminal voltage. So terminal voltage E flux would be equal to EA and some other factor which we will discuss in next slide. So if there is a load connected, then there would be few reasons why EA is not equal to the final output voltage. One reason is the armature reaction. This armature reaction is basically the distortion of air gap magnetic field by current flowing in the stator. So if no load, there will not be any current passing through the stator, so there will not be armature reaction. So if there is a load, armature reaction would occur. Another distortion is self-inductance of armature coil. Third distortion is resistance of armature coil. And the fourth one is the effect of salient pole rotor shape. No discussion in this course means that we are not considering this point in our voltage calculations. We are calculating our final voltage and assuming that the rotor shape is non-salient, or you can say the rotor shape is cylindrical. So out of these four distortions, we will consider first three distortions to model the terminal voltage. We will skip this fourth voltage and we will assume that the rotor is cylindrical in shape. So now we come to the first distortion, which is armature reaction. In armature reaction, when rotor spins, E of A is induced in stator winding. This is quite simple, that voltage is induced in the stator winding. If loaded, a current flows in the stator winding which will produce another magnetic field because of that current flow. The stator magnetic field distorts the original rotor magnetic field, which will change the resulting phase voltage. Now this change is basically, or you can say, the armature current is affecting the magnetic field which has created that current. That's why it's called a reaction, the armature reaction. We see that we studied induced voltage is equal to V cross B into L. E of A is the internal voltage, which is same voltage appears at the terminals of the machine only if there is no current flowing in the stator winding, as we have discussed earlier. Since we have considered that in this part, or in this A section, there is no load connected, so there is no current shown in this diagram. The direction of B and V are obvious from the diagram. Now we consider that the generator is connected to a lagging load. If there is a lagging load, the peak current will occur at an angle behind the peak voltage. If this is the peak voltage, this is the peak current, which is occurring at an angle behind the peak voltage. So the effect is shown in the figure B. So this figure B, as we have discussed, is showing this effect. The current flowing in the stator windings produces a magnetic field Bs of its own. The direction of Bs is given by the right hand rule to be as shown in figure C. This figure shows that this is Bs. This has been calculated by right hand rule. So this stator magnetic field produces a voltage which is written as E stat or stator voltage of its own in the stator, known as armature reaction voltage. So this voltage. So we studied that V of A would not be equal to V of phi would not be equal to E of A if there is a load. So if there is a load, this additional voltage would also be there. Otherwise, if there is no load, then this would be 0 and V of phi would be equal to E of A. So similarly, the net magnetic field is equal to Br plus B of S, rotor magnetic field and stator magnetic field. Now we want to model the armature reaction. We see that there are two main things to consider in this diagram. One is that E state lies at an angle 90° behind the plane of plane of maximum current IA. This is the plane of IA. So E state lies 90° behind it. Another reason is E state is directly proportional to the current IA. So by keeping these 2 points in our mind and supposing that X is a constant of proportionality, then we can write the equation for E state is equal to minus Jx Ia. But we have already studied that V phi is equal to E of A and E of stat. If we suppose that E of stat is this, by substituting the value of E state in this equation, we will get the equation like this. And if we see, this is the same equation which can be found from the Kirchhoff's voltage law of this circuit. So if we find the Kirchhoff's voltage law of this circuit, we will find the same equation which we have obtained in last slide. So this stator coil have also second and third distortion, that is among the distortions, as we have modeled the first distortion, now we are considering the second and third distortion, which were related to the self-inductance and resistance. If the self-inductance is modeled by LA and resistance by RA, then V of phi is given by E of A minus JXIA minus JXAIA, this is because of the self-inductance, minus RAIA, this is because of resistance. So after deducting three voltages from E of A, we come to the final output voltage V phi. But we know there are two inductances, one two uh, in the self inductance we have X of A, two reactances, and another reactance is X. So we can combine them together and give them a name X of S, which is equal to X and X of A. By taking minus I of A common, we can write something like this, and substituting this X of S, so V of phi would be equal to E of A minus J X of S IA minus RA IA. So now we can see that the individual phase circuit is similar to the equation we obtained in the last slide. So this is the same circuit. So the other two are basically the replica of the same circuit, and a constant voltage is applied over here. We also have inductor and adjustable resistor to change the resistivity according to the situation or needs. So these three phases can be connected in either delta connections or Y connections. If we connect them in a Y connection, we can get the same circuit, something like this, which is the same circuit which we have seen in the previous section, just we have connected them in Y connected way, and we can use the same formula which we have studied many times ago for the Y connections. Similarly, it can be connected in delta way to obtain the terminal and final voltages. This is the per phase equivalent circuit. We have already seen the complete circuit, but this is per phase equivalent circuit. The three phases of the synchronous generator are identical in all respects except for phase angle. So there is only the difference between the phase angle. All the three phases are same. That's why we can consider one circuit to study. Since we know that in the problem statements we would be given some phasor relationships, In these phasor diagrams, we will have to calculate and give them some magnitude and direction and angle. So these phasor diagrams mainly have two parts, angle and magnitude. At unity power factor, which is written as PF, at unity power factor the internal generated voltage EA differs from the terminal voltage by resistive and inductive voltage drops. So in this case we have considered that there are resistive and inductive drops, voltage drops. That's why EA is not equal to V of phi. So V of phi is less than E of A because there has been some losses. The upper one is the phasor diagram with lagging power factor, and the lower one is phasor diagram with leading power factor. For a given phase voltage and armature current, a larger, this is the larger, a larger internal generated E of A is needed for lagging loads than for leading loads. A larger field current is needed with lagging loads to get the same terminal voltage because E of A is directly proportional to phi omega. In the real synchronous generators, the winding reactance X of S is much larger than the winding resistance R of A. That's the reason we can neglect this R of A to make the calculations more simpler. So this is for today. Thank you.